Good morning. We shall be talking about a completely different area of physics, except for its electromagnetic waves. That is, we're going to be talking about light. So we're going to start today looking at things dealing with light. So first thing starting off is just basic things about light. First basic thing about light is we treat light as rays. Some of you may have more math than others. What does a ray mean in math? It's a line that, has a direction, but what distinguishes a ray from a line has a starting point, but no end. And so an example of why we treat light as a ray is here with the laser. The laser is shooting out light. The light has a starting point, it's here at the laser, and it would have no ending point except for there's a wall back there. And so where it hits the wall, then it has an ending point. So that would make it a line segment. We call it the ray nature of light because if there was no ending, no wall, no obstruction, it would just keep going forever in a straight line. So we treat light as a ray, as something that has starting point, no ending point. Now, the light, when it hits something, can do a couple things. When it hits the ceiling up there, what's it doing? Okay, back of the room, whatever, wherever you want to look. It's being absorbed. When light hits something, one thing it can do is be absorbed. Another thing it can do is to be transmitted. It can go right through. So if I have the light hit a piece of glass, it'd go right through the glass. Or here, I will make it hit Michaela's bottle. And, okay, I'm not very stable here. But you see it goes through, it still hits the back wall there, even though it's hitting her bottle. So it can be transmitted, or the last thing, I'm going to see if this works. Alex's computer, well, I can't see the right angle. It should be reflected somewhere, but I don't know where it's being reflected. Over there. Okay, so you guys can see it's being reflected. It should reflect better if I can hit wherever that logo is. So those are the things that light can do when it hits something. It can be absorbed, it can be transmitted, or it can be reflected. So when we want to talk about how this works, it actually turns out that we go back to what's really going on with light. What is light? Fundamentally, after James Clerk Maxwell, we understand that light it's a wave. It's an electromagnetic wave. So we have waves traveling through space. And so we're going to look at how those waves are going to be absorbed or reflected. And one of the first things that we have here is the definitional is the idea of a wave front. Now, a wave front would make sense if you're at the ocean and you're watching an ocean wave come in. Because when you watch the ocean wave come in, you see something that looks kind of like that. And if I ask you, where is the wave, what would you say?
Everywhere.
Okay, everywhere would be the correct answer. But most people would answer, and I'm one of them, would answer like Noah did. Well, it's somewhere, let's say about here. And that's what the idea of a wave front is. We say the wave front is going to be the place here where I have the peak of the wave. So I sadly don't have a picture of a nice ocean wave coming in because I love ocean waves. I could sit and play in the ocean all day, watch the ocean all day. It's what I love. But if you have ocean waves coming into shore, you would say, oh, look, there's the wave, and you could trace it. And that's what we're going to call a wave front. So in this picture here, you have ripples. So here's where the source is. And you have ripples coming out, and you could say, okay, here is, I wish I had a steadier artist type hand. Actually, I think that's okay. I didn't actually. It's just reflecting off the front or the back side. So on the front part, I'm on the boundary with the shiny part on the back side. But there's a wave front. What direction is that wave front traveling? It's outward. Or as we like to often say, radially outward. It's traveling outward from the center. So we have a wavefront that's traveling, that's moving. And so when we talk about how waves propagate, how they travel, we will talk about these wavefront, this idea of a wavefront, because it makes it easier to discuss. It's not like a necessary thing. It's a thing to make it easier to comprehend. So here's an example. This picture, circular wavefronts, that's the same as what we saw in the preceding picture. You have the circular wavefronts with waves that are emanating from that central point. What we're going to deal with on a normal basis is going to be more of a planar wavefront. That is this here, which I've now unplugged so I won't accidentally. You should never, ever, 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 ever shine a laser in somebody's eye or look in a laser. Mini lasers are going to be somewhat safe, but it's still really bad practice because oftentimes they're not safe. You know, like those little green pointer lasers? They're usually not safe. They're not very regulated, and oftentimes they will be made using an infrared laser that is then frequency doubled to make it into a visible. And they don't block the infrared, and you can scar your eye by looking in that. So do be very careful with lasers. When I was in graduate school, there was a man I worked with who was working with a laser beam, got no laser power at the end of the beam, and he's like, what's happening? And he looked down the tube. And when you're doing research, you do things to try to keep the laser beam from being spread out so it's not bad, dangerous for your eyes. Well, he looked down the little pipe, and the laser beam was hitting the side of the pipe. Because it was hitting the side of the pipe, it was reflecting off in all directions, so it was really weak, and his sensor was looking for strong beam, so it didn't get it. But it was strong enough, it burned his eye, and so he had very, very poor vision in that eye, just from a moment of, where is the light? Right, so it happens to the best of them. You need to be careful and respect lasers. Don't look into a laser. I don't care what kind of laser it is. Somebody's got a little laser pointer. Don't shine at somebody's eyes. Don't let it shine in your eyes. Okay? Safety thing. Another funny thing, when I worked at the Department of Energy lab, you're supposed to have an eye screening before you start and when you leave to see if you had damage done from the lasers when you're working there. It's basically to protect them from you suing them for damaging your eyesight. I only worked there for 9 months, and I had my initial screening 6 months after I'd come there. And they sent me to one ophthalmologist who did a really careful job. And then when I left, they sent me to this other ophthalmologist that didn't even know how to use his equipment. When we came back, I was there with another guy, and he was telling the lab manager, yeah, Richard had to show him how to use his own equipment because the government really cares. Get a really poor screening when you leave, good one when you start. You're going to end up with better vision when you leave just because of the quality. Anyway, getting back to this. So we're going to be looking at wavefronts like this primarily, where we have a plane wave. The plane wave geometry is easier for us to analyze because you have straight lines for those wavefronts instead of curved lines. Geometry is a lot easier with straight lines. How is it that we're going to have these parallel wavefronts, a plane wave? Well, if you take that ripple, the circular wavefronts, and you get far enough away, that circle becomes bigger and bigger radius, so less and less curvature. So as you take as a gross example, the sun. Light coming from the sun is going out in all directions, so it's forming circular wavefronts. But by the time you get 1.5 times 10 to the 11th meters away from the sun, those wavefronts might as well be perfectly planes. And so we would take the light coming from the sun and say, those are parallel rays. Notice the blue is the rays of light. Those are parallel rays that then make wavefronts. The wavefronts are always the direction perpendicular to the wave's travel direction. They're nice plane waves. And of course, I use the sun as an example, and that's very clear. It's going to be a plane wave. But even if I have a light bulb, so let's take the light bulb up here, get it in the direct path of it. By the time it goes from there to my hand, the waves that are hitting my hand are pretty close to, once again, flat wavefronts. So for all of our experiments, we're not going to be having a big enough angle or close enough to the source to treat it as something that is actually curved, and it'll be easy. We can just treat them as plain waves. Makes our lives much simpler. Now, a question that I did not specifically ask, or answer, but for which, I think I know what happened wrong. Okay, it says it's open for polling. I'm going to trust it, but which I've given you the information that you can answer. What is the spacing between adjacent wavefronts? So this is applying what you've learned from first semester to this. And you'll notice Windows doesn't have a nice shortened form of 3/8 like it has for all the other fractions. That's why it looks different. And Noah, you are the last person who has not been asked a question, so this is definitely coming to you. The channel? That's a B.
I got it.
Okay. Waiting on. There you go. And getting down to the last one. Hopefully it tells either you or me what people answered. All right. I'm just going to write those on your card. Here's our answers. We had no majority, but a clear plurality. So what's your explanation here, Noah?
Isn't it just one wavelength? Because between two different wavelengths,
that's right. Because it's where the crests are, the distance from crest to crest would be the difference between, or the distance between the wavefronts, and that would be one wavelength by definition. So, right, this was a case where I had not specified that. You had to use the reasoning as you did. Oddly enough, apparently I did not stop it. Somebody's still answering, changing their answer. One of the people that said a quarter wavelength changed it to one wavelength after. Not pointing any fingers, but one person was sitting here with this clicker like this. I don't know if it was you or not, honestly. Okay. He was trying. There would have been two people who changed their answer, but it didn't work for him. Okay. So the spacing between wavefronts is one wavelength. Now we get to Christian Huygens principle. When I was in college, my teacher called it Huygens principle. I always pronounce it that way, and then I read up, and if Huygens, okay. So what Christian Huygens said was, as we have a wave traveling, I have a wavefront. Here's my wavefront. So the wave is traveling like this. This is the wavefront. He said this wavefront can be thought of as just a whole bunch of tiny little point sources. That is, if I had a whole bunch of little light bulbs on that wavefront, and the light bulbs were all in phase, that means they're making waves come out that reach their peak at the same time. Then if I added up all of those little light bulbs, the output, I would recreate the light that goes through there. And so basically he said we can treat that wavefront as a source of a whole bunch of little in-phase light sources. So I could say, okay, here's a light source, here's a light source, here's a light source, here's a light source. And these are all in phase. Now that's way too many dots for me to go through and draw for each one. But if I had one light bulb, what direction would the light be traveling away from it? If I have a point source, what direction does the light go out? It goes out radially, so it's going to form, well, in 3 dimensions, spherical, in 2 dimensions, circular wavefronts. So I'm going to draw the wavefronts. And so here's a wavefront, here's a wavefront, here's a wavefront, here's a wavefront. So I'd have like that. And if I add all of those wavefronts together, now that's kind of a hard problem to add them all together. What I'm going to get is a new wavefront that is parallel if I have a plane wave. So Huygens' principle says that I can take each point on a wavefront and treat it as a new source for a wave, and then I can see how the wave is going to propagate by adding together what I get from those sources. Now that seems kind of futile, but let's consider a simple situation. Let's say that I have a wave that's coming up on something that blocks the wave. So here's an object that's going to block the wave. This is why I had this highlighter set to black. So I can go So I have a wave that's going to come and hit that. So my wave is coming. And using Huygens' principle, I can say, okay, there should be a wavefront right here. I just put my wavefront there. And what does Huygens' principle say I should do? Treat each point on the wave as if it's a source for a new light source. So I'm going to put some sources here. And then I'm going to show the wavefronts produced by each one. So now if I combine all of these, add them together to get my new wavefront, what's my new wavefront going to look like? What's going to look like in this region out here? It's going to be a straight line. But what's going on in the region down below my straight line here? It's curving around because there were no additional sources. So when the wave goes past that barrier, it will bend around the barrier. That is a direct outcome of using Huygens' principle. Now, you know that to be true with sound. You know that if I'm outside with the door open, I don't have to be direct line of sight with you. You'll be able to hear me because the waves will bend around the doorway. But with light, and I just said line of sight. If I'm not line of sight through the doorway, you're not going to see me, right? So it seems like the light waves don't bend, but they do. It's just they don't bend nearly as much as sound waves. And that's because of the wavelengths. The wavelength of light is very short. Wavelength of sound is very long. It makes a difference for the bending. And we can go through using Huygens' principle to calculate just how much intensity we have bending around. And as you would guess, we'll have virtually no intensity going this way, more intensity going like that. And so the amount of intensity that's bending depends on where you are on the bend and the wavelength. So that's a very practical application of Huygens' principle. Now we're going to see some more applications of Huygens' principle in a few moments. These are links that clearly aren't going to work here to sources that you can look at for additional help in understanding these ideas. I'm not going to go through them in class, and instead I'm going to continue on and talk about our geometrical optics. Geometric optics is a term we use for the simple optics where we can use geometry to describe what's going to happen. Things like when I have a reflection, we can use simple optics. When I have refraction, I can use simple geometrical optics. So we can use this geometrical optics using geometry to help us. So this means we're going to have to come back to the geometry, things that we've been talking about a lot when we broke vectors into components. Well, now we're going to use it again, but a little more intensely. And we'll start with light reflecting. When light comes down and hits a surface, we have what we call the incident rays. Incident means coming in. So incident ray is a ray of light coming in to hit a surface. And I said earlier in the lecture, when light hits a surface, it can reflect, or it can be absorbed, or it can be transmitted. Right now, we're going to focus on reflections. When the light hits that surface, you can actually use Huygens' principle to show that you're going to create wavefronts that reflect off such that the angle of this wavefront with the surface is reversed. So if it comes in with a wavefront like this, it's going to reflect off with the wavefront that's reversed. That's not the way we talk about it, though. Now, I'm not doing the geometry here. It's not very hard, but it's, I think, pretty self-evident that when light comes in and hits a surface, it's going to reflect off symmetrically. So using Huygens' principle, you can actually mathematically show that it has to do that. What we're going to do instead is describe what we call the mirror equation for specular reflection. Oh, perfect. Specular reflection means mirror-like reflection. So for you and me, when we say specular reflection, we mean it's reflection like it hit a mirror and bounced off. When light hits a mirror and bounces off, we talk about the incident beam, the reflected beam, and we draw a normal to the surface. I know I have this drawn somewhere. A normal to the surface. A nice smooth hand would be a real benefit. So there I drew a line that's normal to the surface. What's the difference in the words normal and perpendicular? Yeah. Normal involves a surface, perpendicular involves a line. So in pictures like this, the normal looks perpendicular because it's a two-dimensional picture. But if I have my desktop, I can't describe technically a perpendicular to this. I can only describe the normal to it. So that's the difference in the words. So I've got that surface normal, and we measure two angles. The angle of incidence, and I'm just going to use I for incident. Well, no, I'll use INC, okay. And the angle of reflection. You actually have to go out to the fourth letter when you put the angle of reflection, because there's another thing that we're going to learn about soon that's called refraction. And they both have REF as the first three letters. So you have to go to the fourth letter to make it unique. So the angle of reflection, the angle of refraction, really, really important. What is the angle of reflection measured between? What two things? The normal to the surface and the incident ray. I hope I said angle of incidence, not reflection. Okay, so the angle of incidence is from the surface normal to the incident ray. The angle of reflection is likewise from the surface normal to the reflected ray. And you may think, why is it so important that we have that definition? With reflection, it turns out that it wouldn't be a problem. With refraction, it is. So we have to make sure we do it a consistent way so we don't make mistakes. So always measure the angles from the surface normal to the incident ray, from the surface normal to the reflected ray. And the law of reflections is very simple. The angle of incidence is equal to the angle of reflection. So if the light comes in at 30 degrees from the surface normal, it's going to reflect away at 30 degrees from the surface normal. And that's what's going on with a specular reflection. Now we're going to look at some geometry. You'll probably have a few geometry problems in the homework that deal with this. Specular reflection isn't the only kind of reflection. Here's a second kind of diffuse reflection. A diffuse reflection is a reflection where the light gets spread all over the place. Now we can analyze this real easily. Specular reflection is a mirror-like reflection. When you look in a mirror, so Angelina, you look in the mirror, you see yourself?
No.
No. Now you see yourself?
No, what?
That's just my angle of holding it. You see yourself now?
Yeah.
Okay. You see yourself in a mirror. With a specular reflection, you can see recognizable things. They give you an accurate reproduction. With a diffuse reflection, you can't see those things. So if you look at, let's say, my shirt, can you look in my shirt and see yourself or somebody else reflected in it? No. Then what kind of reflection must it have? Diffuse. I say what kind of reflection must it have? Why does it have to have a reflection? Because you can see it. You see light coming from things. So you see light coming from my shirt. But my shirt does not glow in the dark. It's not producing light. So all the light you see coming from my shirt is reflected from the light hitting it, coming, from the lights ultimately in this room. So you're seeing reflected light off my shirt, and that's a diffuse reflection because you can't see things like you would in a mirror. And I usually use my forehead. Can you see yourself reflected in my forehead? No. So that means that my forehead is giving you a diffuse reflection. Now, why does my forehead or my shirt give you a diffuse reflection where the mirror gives you a nice specular reflection? The answer is on my slide here. It has to do with how smooth the surface is. If the surface is smooth, as shown there, smooth surface, then you get a nice specular reflection. If the surface is rough and pitted, and my forehead is pretty rough and pitted. It's got all of those little pores that produce sweat and oil and whatever. So when light hits those, every place that light hits, it's actually going to follow the law of reflections. But the angle of incidence and angle of reflection are based on the normal to that little piece that it hit. So for instance, if I look at the normal direction here is like that. The normal direction here is like that. The normal direction varies depending on which part you're looking at. And since the normal direction varies, that means the reflected angle is also going to be varying. So the roughness of the surface is what makes it have a diffuse reflection. Now, I don't know why, but the more I read, actually, flat earthers have been banned from at least one of the creationist Facebook groups I follow, so I've been giving less exposure to the flat earthers. But I've been reading a lot of their arguments, and one of them is about the moon. What do flat earthers believe about the light coming from the moon? Do you know? Well, from my exposure, they believe that the moon is a light source. That the moon is not reflecting sunlight, that it's a light source. I don't know how you explain the phases of the moon by that. It doesn't make sense to me. But to them, it makes sense that the moon is a light source. It's like the moon's a light bulb out there, the sun's a light bulb out there. And one of their arguments to show you clearly why the moon must be its own light source is what happens if you look at, let's say, a nice reflective steel ball, because we scientists say that the moon is a reflective ball. If you look at a nice reflective steel ball and you have a light over here, what do you see for the reflection off of that steel ball? Because the angle is constantly changing, only at one specific angle are you going to have it bounce just right, and you'll see that light source is just a little spot, and the rest of it won't have much reflection. And they say, so how is it that we should see the whole moon? That's impossible. Well, what are they missing in that let's say, first grade analysis of the moon's reflection. It's what? That is something they're missing. That's why I don't know how they explain the phases of the moon with this. Because yeah, that's a big glaring hole. But there's another one that's relevant to what I'm talking about here that they're missing. I heard change there, I heard rough surface. I'm going to go with what she said because I'm not sure you might have been going there. The rough surface. The moon is not smooth like a nice polished ball bearing. The moon has a rough surface. And because it has a rough surface, what kind of reflection are you going to get from the moon? A diffuse. Well, that diffuse reflection, because of the rough surface, spreads the light out in all directions. So you shouldn't have the kind of reflection that you would have off of a ball bearing from the moon. If you took a piece of steel and drop forged it and you get this really rough surface sphere, well, yeah, it would look something like that, which would shine up all over the place because light's hitting all over the place and reflecting at random angles. But, once again, it's not worth your time, energy, or the electrons that you're sending down the pipe to try to explain that to these people because they have already decided that it is just impossible. But yeah. Moving on from that, if nothing else from this class, you'll learn that I do not believe in a flat earth. Question, Erika.
Wait, so then, just to, can you explain this better to me, but you know how the moon isn't all, it has lots of indents and crater areas and stuff, and it still reflects the light, then what allows it? Would it just be the type of light?
Say that again. The moon has a rough surface.
Yeah, so it would be more of a diffused reflection.
Yes, right.
But it's still pretty bright, and we know that it's shining. So what causes it to just? Okay,
so the moon is still pretty bright. The moon, the albedo of the moon, that is its reflectivity, is somewhere around 0.07. It reflects somewhere around 7% of the light that hits it. So the moon is going to be much, much fainter than the sun because it's reflecting only a small fraction of the light, first thing. Second is, anywhere the sunlight is hitting, it's going to be scattered in all directions. So we're going to see light coming from everywhere on the moon that light is hitting. Because of the roughness of the surface of the moon, you have things like sometimes you'll have a crater and you'll have a shadow for part of the rim of the crater because the sunlight's hitting it at an angle. And we see those shadows when we look at the moon. We have variations in the material and the albedo on the moon. That is, some areas you have a breccia surface. A breccia surface is like rock that is angular and has been pushed together. So I'm sure you guys aren't really into the difference in a conglomerate and a breccia. The conglomerate is what you form in streams where you have water cause stones to tumble and be smooth, and then they get kind of cemented together. Breccia is where you did not have them smooth and they're cemented together. So you have breccia in parts of it, and then other parts are basically just a powder. And so you're going to have different reflectivities from those. So some parts will be brighter and some will be fainter just because of different types of materials. So what we see at the moon is a combination of a whole lot of things that are very much applicable to what we're talking about here. First, Corso, what was your question?
I was just talking about the Earth being flat. I didn't have any question.
Okay. Gila.
So are we just far enough away from the moon that the light that's being reflected off of it seems like a straight wavefront to us?
Yes, it will seem once again like a straight wavefront to us. And yes, there was something here. Specular reflection is more important in optical instruments. Yeah, I didn't get that on my slide. And moving on, second clicker question. When you look at the face of a friend, what kind of reflection do you see from his or her skin? Okay, everybody's answered? Everybody answered the same. Everybody said diffuse reflection. This is going to be the easiest thing in the world for you, Gila. Everyone said diffuse reflection. Why?
Because a face doesn't reflect with a mirror, so therefore
Okay, so she used the direct observational because you don't see the reflection of somebody's face or of your face on somebody else's forehead, then it must be diffuse. The other answer would be because we know the surface is rough. Well, if you look at some people's foreheads, and mine's probably a good example, I'm not sweating like a fiend right now, but often I am, you see a glare off of the head, right? What causes that glare? That glare is actually a partial specular reflection. Well, how can the pores and everything on my face give us a partial specular reflection? Yeah. You form a fluid layer over there, and that fluid has a smooth surface that'll reflect, maybe 5 to 10% of the light. And so that's what gives you the glare. And so like if my skin was perfectly dry, you wouldn't get that. Or if I were to powder up my skin, like Gila does a lot of acting. I don't know if you guys have enjoyed her acting skills. I've missed it every time, sorry. But I know she's in plays all the time. And one of the things that you do is you put on copious amounts of makeup, which drove me crazy when I was doing plays. And part of the reason is you've got all those stage lights and you don't want, people to get blinded by the light reflecting off of your sweaty forehead. So you put lots of powder on there so that you don't get that reflection. And then once you put the powder on, you have a pancake face and you have to put other stuff on to bring back, it's crazy. Okay, I've already covered the next few slides here. There's the picture that shows the angle of incidence equals angle of reflection. Just use one letter, which is fine until you get to refraction. And now a question that I said was super important. How do you measure the angle of reflection? From where to where? Got an answer for me, Etika? There we go. Okay. A little bit concerning to me. I thought I was really, really clear on this, but apparently not. Ashley, how do we measure the angle of reflection?
I don't know. It kind of tripped me up because I definitely said C because you were talking about the normal, how it needed to be normal to the surface. But you said it was concerning that all of us chose that.
No,
So,
it's concerning that 3 people didn't choose that. No,
But yeah.
no, you should go with the one you understand, because if you're wrong, then you'll find out why.
Yeah, I chose C because we talked about how it needed to be normal to the surface.
Okay, yes, it needs to be measured from the surface normal. And as I said, if you're actually talking about just reflections, it would be, you would get the same answers if you measured this one.
Okay, yeah. So.
You would get the same answers, but when you go to talking about refraction, you wouldn't get the same answers, and that's why that's not the correct way. So it's very important to do it this way. This first one is called the deviation, well, kind of, going from the incident ray to the reflected ray, and it is not the angle of incidence or the angle of reflection. So, to summarize what I've said about reflection, the angle of incidence equals the angle of reflection for which kind of reflection? For specular reflection. And what's a more explanatory term for specular reflection? Yeah. Mirror-like reflection. So for mirror-like or specular reflections, the angle of incidence will equal the angle of reflection, with the angle of incidence and the angle of reflection both measured from the normal to the surface, and the reflected ray lies in the same plane as the incident ray. This is a correct statement that once you understand it makes perfect sense, but it's a little hard to really define it. What that's saying is that all three of the lines shown here, the surface dashed line, the reflected ray, and the incident ray are all in the same plane. So I can make a plane here that's perpendicular to that line in the surface. And all of these are in that plane. So they're all, if it was a piece of paper, all of them would be drawn on that piece of paper. Right? So you're not going to have it come in like this and then go out like this, is what that's saying. If it comes in like this, it's going to come out like this in the same plane. So those are the two laws that go together for mirror reflections. Now I believe we're going to do some examples. So you want to stand in front of the mirror and see your reflection. How much mirror do you need? Well, this picture kind of shows you, but let's talk it through. I used to have a clicker question that started by asking how much mirror do you need to see your reflection in the mirror? And what would the normal thing come to your mind that would come to your mind be? Like if you're going to put a wall mirror in your house so you can see your entire body in that wall mirror, what would be your parameters for how high you want to go and how low you want to go? Okay, I heard your height, you for the top, right? How low would you want to go? To your toes. Most of us would like that wall length mirror to come pretty close to our toes and all the way up to at least the top of our head. But it turns out that's not the minimum. That is twice the minimum. Because when you look in that mirror, light reflects off of your foot, comes up and hits the mirror, and based on the angle of incidence being equal to the angle of reflection, if your eyes are the same distance away from the mirror as your feet, then you're going to have two similar triangles here. Wow, let's not even go with that. Two similar triangles. This distance here then must be the same as this distance here. So the distance from your eyes to where you're going to see your feet on the mirror is 1/2 of the distance from your eyes to your feet. Now, to make life easy, we can pretend our eyes are in the very tip of our head, and the difference between the tip of our head and our feet is 1/2 of our height. So if your eyes are on the very top of your head, you would need 1/2 of your height to see yourself in the mirror. Your eyes are down here, well, then I need a little less than 1/2 of my height below, but I need 1/2 of the distance from my eyes to the top of my head above to see the top of my head. So it turns out that in all cases, you need a mirror that's 1/2 of your height to see your entire body if you're standing vertically with your eyes directly above your toes and with the mirrors vertical. So why then do wall length mirrors not start at, I am about 6'2.5", so let's put the top of it around 6 foot. That should be about halfway between my eyes and the top of my head. And the bottom of it at about 3 feet. Why don't we just put it from 3 feet to 6 feet? Some people aren't the same height as me. If Gila were to stand next to me, she's not as tall as me. All of that part that's above her head would be wasted space, and she wouldn't be able to see her feet because it's not going down low enough. So you want to have a short person, like 7-year-old, to be able to look in there and see their feet. And you want to have a tall person, somebody who's 6'8". You know what? They don't build anything for a 6'8" person. I'm not 6'8", so I don't have to worry about that. But in your bathroom, they put the top of the mirror at, I don't know, 5'8" or something crazy like that. So I want to do something silly like, I don't know, shave. And when I shave, I have this odd thing that I actually want to see when I'm shaving. And so to shave, I have to do this action so I can see where I'm shaving. Because if I'm lit, if I stand up, I can't see anything above here. We actually got the mirrors put higher in my house when we redid it this summer, so I don't have to do that anymore. It saves a lot of back pain. So, that's why the mirrors have some range. And if you ever design a bathroom, make the mirror tall enough that somebody that's 6'8" can see themselves. Just be good about that. Make the shower heads, by the way, high enough that somebody can stand underneath them. It's really convenient and rare to be able to stand underneath the shower head. Multiple reflections. Let's do this bad boy. Here we have an example of a right angle mirror. And what I want to know is, how much is the light wave going to be deviated that reflects back compared to what I sent in? So I send in that light wave on the bottom, and it's going to reflect not once, but twice. How do I find the angle difference between this and this? Lead me through. Go ahead, Vlad. It involves, by the way, a lot of geometry in the rest of our class period. Triangles, yes, involves triangles. If we had more than 3 minutes left, I would have you work in groups to do this, but we don't have too much time, so I have to lead you through. So first of all, what we have is, what's the relationship between theta 1 and theta 1? They're equal, right? That's why the picture has them both labeled theta 1. How much deviation do I have for this first reflection? Okay, 180 degrees would have been straight. How much do I have to take away from the 180 degrees? I have to take away 2 theta 1. So that's how much it deviated at the first surface. Now it's going to go to the second surface, and at the second surface, it would have come like this. It has this much deviation. What's deviation 2 going to equal? Anyone who followed Gila? It's 180 degrees minus 2 theta 2. Well, now what I need to do is get this in terms of, well, we have a right angle here. So in terms of this angle that I'm going to call phi. So how do theta 1, theta 2, and phi relate? I'm going to redraw this big triangle here. Start with something simple. What's this angle going to be? (90 degrees minus theta 2 is the direct way to determine, because I have a right angle between my mirror and its normal, and theta 2 is the angle between normal and that ray. So the angle between the mirror and that is 90 degrees minus theta 2. And over here, it'd be 9 degrees minus theta 1. And we know that the sum of the interior angles, sum of interior angles of a triangle, is always 180 degrees. So that means I can make an equation that says 90 degrees minus theta 2 plus 90 degrees minus theta 1 plus 90 degrees because of the right angle has to equal 180 degrees. Does that work out? Now, actually, I wanted to put in the angle phi here because I was saying let's do it for general instead of for a 90-degree angle. So plus that angle phi is 180 degrees. Well, conveniently, what's 90 plus 90? I saw Jeff going to scratch his back, and I thought he was raising his hand. I was like, well, yeah, he knows it. 90 plus 90 is 180, so I subtract those out. And what I'm left with is theta 1 plus theta 2 is equal to phi. So now I come over here, the total deviation is equal to deviation 1 plus deviation 2 is equal to 360 degrees minus 2 times theta 1 plus theta 2. Well, 360 degrees is no deviation, right? Because that's just back to where he started. So this 360 degrees I can cross out because that is no deviation. And my total deviation is minus 2 theta 1 plus theta 2. But theta 1 plus theta 2 is phi. So my total deviation is minus 2 phi. Why minus 2? Well, that's just the direction. The minus sign is really unimportant to us here. 2 phi. So if this was a corner cube, if that was a right angle, phi would have been 9 degrees. The total deviation would be 180 degrees. So if you have light come into mirrors that are 90 degrees from each other, if it reflects off both surfaces, it will always come back exactly the opposite direction it came in, which is what's depicted in this picture. Okay, that's enough geometry for today. We'll do more geometry on Friday.